We just determined how to measure a rate for a reaction, and one of the and in addition to that, we talked about the different things that can impact the rate of a reaction. And one of the things we mentioned was, when I say we mentioned, I should say what I mentioned was that concentration of reactants sometimes can, and most times can, impact the overall rate of the reaction. Okay? And this relationship can be summed up by something we call a rate law. And the rate law is of a reaction. It's a mathematical relationship that tells us how the rate changes as a function of concentration of our reactant, where in this case I'm saying the reactant is represented by A, right there. The rate law is something that you can't just look at the balanced reaction and tell what it's going to be. The rate law is something that must absolutely, without question, be determined experimentally. It's not something you can just figure out by looking at a balanced reaction or thinking about the reaction. You have to determine it. You have to run some reactions, measure their rates, change concentrations, and see how the different concentrations impact the corresponding rate. Now, the rate law itself um, would look something like this. And I'm going to add one more thing to it. It says the rate law for the reaction, for this reaction, would have the form given below. Well, I'm going to be more specific since we have the two reactants. Okay, I'm going to throw in B, and I'm going to put in M. Okay, so what we get from this, N and M, even talks about it, are the what we call the orders of the reaction, the orders of the reactants, and K is a proportionality constant. Okay, it's a proportionality constant known as the rate constant, and it helps further define how the concentrations impact the rate and how changes in concentrations would lead to changes in a corresponding rate. So let's investigate this. First of all, what do I want you to get out of this real quick is, anyway, those are called the orders. What I want you to get out of this is every rate law, a pure rate law, looks like this, has these types of parameters. And instead of N or M, you'll see later that for us, we're going to say N could be 0, N or M, either one could be 0, 1, or 2. There are other options, but for this class, that's what we're going to do. So as I just said before, the exponent, which is the N or M that I just referred to above, in the rate law on each reactant is called the order with respect to that reactant. The sum of the exponents is called the overall order of the reaction. I tend to say the overall, but you could just say the order of the reaction. Okay? In this case, we'll give you an example. So let's say we have this reaction, then and experimentally, the rate law was determined to be rate is equal to the rate constant times NO to the second power times O2. Now, by coincidence, whoops, didn't mean to do that. I wanted to use my highlighting function. Here we go. by coincidence, there is a 2 there, and there is a 2 here. But I want you to understand. Whoops, man, I am just messing up. I'm hitting the wrong pins here. Sorry. I want you to understand something. They don't have to be the same number. So you simply can't say, oh, because there is a 2 here, that means there has to, the order is second order. You can't say that. You have to, it's just coincidence in this case. This could have been a 1. And just like this also is, there's a 1 in front of this. You know how we don't write it. If there's a 1 and there's a 1 up here, that's also coincidence. There doesn't have to, they do not have to correspond. In fact, if you just simply say, oh, the 2 goes there and the 1 goes there, if you do that, you're going to be wrong 9 times out of 10. Because that's not how you determine the order. It just happens to be coincidental here. So we would say then that the rate changes with the square of the concentration of NO, and the rate changes directly with O2. So there's a squared relationship, and in this case, there's just a direct relationship. Okay. When something has a 2 by it like that, we say it's second order with respect to whatever that reactant is. In this case, it's nitric oxide. And in this case, since there's a 1 here, we just leave it off, we don't write it, but technically there is a 1 there. We'd say it's first order with respect to that concentration of oxygen. And then to get the overall order, we add them together. That's 3 together. All right, so let's look at how you actually find the rate law. Okay, there's a few methods we can use, and I'll show you them. The first one we're going to cover is what we call the initial rate method. And just a reminder, rate laws have to be determined experimentally. The rate law shows how the rate of a reaction depends on the concentration of the reactants. Not the products, just the reactants, okay? Because we're using initial rate. No products have technically really accumulated because we're looking at the rate just at the very beginning of the reaction. So we focus only on reactants. If we change the initial concentration of the reactant, so let's say we measure a rate at 1 concentration of the reactant, then we change it. The initial rate with the new one will be affected. Could be affected, I'll say. Could be affected. And so, in fact, I'm just going to put in parentheses, it doesn't always affect it. And we'll learn what I mean by that later. There's something called zero order, and I'm about to show you that something zero order, you're not going to see any change in rate. So let's examine order first, okay? Let's think about what it means, and I'm going to give us, I'm going to write these down. So let's say we had a zero order reaction. In other words, I'm going to say, what if the rate was equal to K times A to the 0th power? Or we can just simply write it as rate is equal to the rate constant, K. I can do that because any number to the 0th power is 1, right? Any number to the 0th power is 1. I should probably make my 1 a little better here. Okay, and so A to the 0th power is equal to 1. All right, that's what zero order means. So if we change the concentration of our reactant and then measured the rate would remain constant. It would never change. It's independent of reactant concentration. So that's the one example, and the reason why I said could, because if it's zero order, it's not going to impact the initial rate of the reaction. It only does if it's not zero order, and that's these other two examples. So in this example, rate is equal to the rate constant times A. And you don't write to, I'll put to the first power, but really in practice, we don't write that. We just say that. And so if you were to double the concentration of A, the rate of the reaction also would double because they're directly proportional. See? If you doubled that concentration, then you would double the rate. That's what that says. Okay? Whatever you do to this, that's what would happen here. If I tripled the concentration of A, if I tripled it, also would triple. Because they're directly proportional. Okay? So let's look at the last case that we're going to examine in this class, where the rate is equal to K times A to the second power. We call that second order. And what we're saying here, if we double the concentration of A, we would quadruple the rate of the reaction. So the way it is if you change concentration of A, the rate will adjust to the square of whatever that change is. Okay? So if we change A, we'll square that to get get to the rate. So let me show you what I mean by that. If we take 3 times the original concentration, so if concentration of A gives us some rate, then if we took 3 times the concentration of A, it would be 9 times the rate. If we did 4 times the concentration of A, then it would be 4 squared times the rate, which would be 16 times the rate. So that's what this means, and it's hard to wrap your head around it the first few times you hear it, so you got to do some practice here. The idea is whatever you do, that depending on these scenarios, okay, when you're zero order with respect to the reactant, then concentration does not change the rate. When you're first order with respect to the concentration of substrate, then when you change it, let's say you double it, then you also double the rate. If you tripled the concentration for first order, then you would triple the rate. So it's a direct proportionality. In the case of second order, whatever you do to A, you will multiply the rate by the square of whatever that change is. So if I double A, then I would do, the rate would change by 2 squared, multiplied by 2 squared. The rate would, if you tripled A, then you would 3 squared, or 9 times the rate. That's how the rate would change. That's what these rate laws tell us. And we can look at how changing the concentrations will impact the rate, and by doing so, we can figure out which order we're observing for our substrate. So let's use that method then to determine a rate law. So the general idea is we'll run an experiment where we change the reactant concentration, and then measure the change in the overall rate. Okay, and we do that depending on what we're looking at. If we have multiple reactants, we would do one reactant at a time. So before I do this practice problem, I'm going to do another practice problem that's a little easier. Okay. I'm just gonna give you a for instance. Okay. Oops. Let's just do a simple kind of fake reaction where I say 2A goes to product P. Okay. 2A goes to product P. That's our reaction. So let's say I run it one time where here's my reactant concentration. I'll do that in moles per liter. And then we'll do the corresponding rate that we measure. That will be in, we'll say, just for fun, we'll say molar per second. All right. So let's say we then let's do 3 experiments. So, or 3 trials as well. Do 3 different trials. So we'll call it trial 1, trial 2, and trial 3. And I'll put down the concentrations, okay? So trial 1, let's say we used 0.100 molar. And then trial 2, let's say we use 0.200 molar. And trial 3, let's say we did 0.300 molar, okay? And then we measure our rates. And the rates are in molar per second, all right? So in this case, let's say when we had 0.1 molar reactant, let's say we got 15 molar per second. And then when we did 0.2, we got 30 molar per second. And then when we did 0.3, we got 45 molar per second. And I'm going to ask you then, what is the rate law for this? Okay, that's a typical kind of question you might get. And and if I was in my research lab or something and I wanted to determine the rate law for the reaction, then I would actually do a concentration dependency study. Do it all the time, actually, in my lab. This is a very common thing to do. So how would I get the rate law? Well, I know that rate laws take this form, rate is equal to K times the concentration of A to the nth power. Well, what this data allows me to do is it allows me to look at, okay, when I double, look at this. When I double this, what happens to, so that's 2. I take the big number, divide it by the small number. I do the same thing here. I take, because I use trial 2 and I divide it by trial 1, I also get 2. So when I doubled my concentration, I got a doubling of the rate. Well, let's look at this case. I between 1 and trial 3 and trial 1, if I take the big number and divide it by a little number, I get 3. Okay? And if I do the same thing, I also get 3 for the rate. So when I tripled the concentration of the reactant, my rate also tripled. Well, that's the example where then N, because the change that occurs is directly proportional to the rate. So the change in rate that occurs is directly proportional to the change in reactant concentration. I know that N equals 1, first order. So what that means is then my full rate law is K is equal times the concentration of substrate, not substrate, sorry, of reactant to the first power. Now, there's one more thing I can do with this, okay? I can now determine what the concentration of K is. I'm not the concentration, what the value for it is. All I have to do is select one of these data sets, just one of them, one of the trials, and plug in the numbers and solve for K. So I'll try, if I try trial 1, okay, so I'll try trial 1. I got, whoops, I'll just plug in my rate, 15 molar per second is equal to K times, and I'll just put in my value of 0.100 molar. And I want to know what K is, so I divide both sides. And I get 150 molar per second per molar. Well, the molars cancel out. So in this case, K is 150 reciprocal seconds. S to the minus 1, or I could put 1 over S. I can plug in the second, trial 2, and do the same thing. So if I do trial 2, I got 0.2 divided by 30. Sorry, I did it. I did it backwards. Sorry about that. All right, sorry. I got my rate is 30 per second, a molar per second, and I'll be dividing that, and that's equal to K times 0.2. And if I do the same thing, guess what I'll get? K is equal to 150 reciprocal seconds. And guess what I would get for K if I did that one? Same thing, 150 reciprocal seconds. So K, the rate constant, is a constant. There's a reason why it's called a constant. It doesn't change, and it's independent of concentration. Rate changes as a function of concentration. K doesn't. And so the K would be this. So if I really wanted to write the complete rate law for this one, where I include it all, I would say rate is equal to 150 reciprocal seconds times the concentration of A, and since it's to the first power, I just leave it that way. So the rate law, the full rate law, is that. And so what this allows me to do then, and why it's pretty useful, is let's say I wanted to to have a reaction go at a particular rate. Maybe it's an industrial, kind of application where I need a certain rate for a certain reason. Maybe I got to make a certain product at a certain rate for some process. Well, I can look at the concentration and say, let's say I want to know, let's say I wanted a rate of 55 molar per second. Well, I can then calculate what concentration I needed to give me that rate. So the rate law tells me how to do that. So I can just solve for A. Things like that you can do. And so that's one of the reasons why it's helpful to have a rate law in place. Now, in a case where you have two reactants, here's two reactants that I have. I have NO2 and CO. So I got them here, okay? And you do a bunch of experiments and you measure the corresponding rates. But what you do is you have to make sure that to do the reaction, to really look at it, you need to hold one of them constant while you vary the other. So in this case, we see a change here in rate. I hope you notice that the change in rate we see is 4. It increases by 4. I take the big number, divide by the little number. Well, that's not because of this. The CO isn't changing at all. So there is no impact of CO on rate. So the change that we're seeing has to be because the only thing we're changing in this case, we're doubling that concentration. So we doubled the concentration of NO2, but we get a 4-fold change in initial rate. The change is 2 squared. You change 2, and that 2 times 2 is 4, or 2 squared. So because the rate changed with the square of the change in reactant, we can therefore conclude reactant NO2 is second order. Okay? So let's move on to the next page and continue this problem. So the solution, you simply, and what I'm going to say is largely written also down here, but just like I demonstrated, we find 2 examples. I mean, we could have picked any 2 of these where they had the same concentration and then looked for where these things changed. So we did this one. We said that's a factor of 4 when NO2 was changed by a factor of 2. We can do a similar thing. Let's find where the NO2 is the same. So, in fact, to help us, I'm going to highlight the ones that are the same. Okay? And then for the second experiment, we have constant NO2, and we change this by a factor of 2. See, we doubled it. And what happened to our rate? Didn't change at all. No change. So when you change the concentration of CO, it doesn't lead to a change in the rate at all. That means if we look at our data now, we can say that NO2, oh, sorry, let me say this differently. We can say that, well, actually, I think it's said down here, so I'm going to just let it do it for us. When we double, when we have constant, this is showing exactly what I was going to say. When we have constant NO2, we get a fourfold increase in our initial rate. When we double this, we get a fourfold increase in this we just ignore. We get when we double at constant NO2, we double CO and we see no change in rate. So what that means is that we are second order with NO2 because, so in other words, we got this going. And since we got no change with CO, it's zero order. Because rate doesn't change. So here's the rate law that we get. So remember, because this is zero order, we can drop it. So we can just use our rate law as being rate is equal to K times NO2 squared. Okay. Now what is the value for K? Well, we can plug in one of the data sets. So let's plug this one in where we have 0.0021 is the rate and 0.10 is the concentration. And that's this top one here. So we just plugged it in, and this was the rate that occurred when NO2 was at 0.1, concentration 0.1 molar. But since there's a squared term here, we square this. Okay, we square this and divide it into the rate. That's what we're doing here. And our rate constant is 0.21 reciprocal molar reciprocal second. Notice, I don't know if you remember this, the last example I did prior to this, where it was first order, it was just reciprocal second, and there was no molar. So you gotta carry your units and make sure they cancel out. Every time you do this, K could very well have different units for different data sets. Now, what I'd like you to do is go back to the original, to the data set from which this came, plug in another 2 or 3 datas, or just another 2, and you should get the same number for K for each of those, because K is, a constant, hence a rate constant. I was going to have you do this, but I just kind of worked it out, and I realized it's going to give you something slightly different. Like, remember when I said that you don't always have just first, second order? This would be a case where some of the examples are there, so don't do this example, okay? We'll do some in the workshop, and you can also do some Alex problems that will help with that. So that's the end of this part.